ये बात कर ले, मैं केवल वन वे कर लेता हूँ। मेरा आवाज आ रहा है? चैट बॉक्स में यस लिख के भेजना अगर आवाज आ रहा है तो। लिख करके यस लिख के भेजना चैट बॉक्स। यस आवाज आ रहा है ना? ठीक है ठीक है। मेरा आ जा रहा है जो उधर से नहीं आ रहा, चलेगा ठीक है, बाद में देखते हैं। Okay, what I will do, I'm not able to listen all of you. So if any difficulty, you just type in chat box, right? Fine. Just say yes. Okay, fine. So I think in last lecture uh, we have seen the construction of expression trees, right? Am I right? Yes, Dhrumil. Yeah, we have seen construction, but we have not yet seen how to evaluate that construction tree, expression tree. Sorry. Okay, so what I will do, I will just revise the construction of expression tree in Python, and then we will immediately go with the evaluation of expression tree, right? So as you know that how to construct an tree, I will just tell you. Yeah, suppose, okay, I will first share my screen. Are able to view my screen? Just write yes in chat box. Anyone? Okay. So I think suppose if this is our ABC plus star, right? If this is our postfix expression, what we were doing, we were creating a node A, B, and C, and then the last two nodes BC and plus. So in between B and C, we are creating one node plus, and then star and like this tree we are creating, right? So this is called as expression tree, right? Okay, so manually we have seen that what is to be done. First take the scan the postfix expression, then whenever you encounter any operator, whenever you are encountering any operator, then you have to pop the previous two nodes, then one will be the left node, other will be the right node of this operator node, right? So when you read first A, you will push onto the stack. When you read B, you will push onto the stack. When you will read C, you will push onto the stack. When you read an operator plus, then you will pop the two elements from the stack, and the first one will be the left and the second one will be the right, and a new node will be created for this plus symbol, right? And in this way we proceed. So let us see the program for that. For this purpose, we are having a function construct to which we are passing a postfix expression, right? And we are making use of deq, that is dq, right? Which is working as a stack. Although it is double-ended queue, but I think I have made it very clear that I will be pushing from the same end and popping from the same end. That's why even though the name is queue, it will working as a stack only. So we are using a for loop for scanning each and every symbol in that postfix expression, right? So first we will check if it is operator. Definitely, initially it won't be the operator, because if I write ABC plus star, the first two symbols at least will be not operator. So initially this condition won't be satisfied and you will come into the else part. So whatever operands you are reading, that operands are added into the stack, are pushed into the stack, even though the function written here is append, but it is working like a pushing the element into the stack. So whenever you are reading operands, the operands are pushed onto the stack, and then a time will come when you will read an operator. Just like here we have seen that after reading A, B, and C, we will read plus. Okay. So when you will read plus, this is operator function will be valid, will be true, and then you will come inside the loop where you are popping the two nodes, one X and other in Y, and you are creating the new node, right? You are creating the new node, and then that new node is appended in the stack. Okay. So in this way, what we are doing, we are creating a expression tree, right? We are creating an expression tree. Okay. Any problem in this? You may write in chat box. If there is no problem, few of the students write yes or no. Any problem? No. Fine. So now let us try to evaluate the expression tree. Okay. We will take one or two examples manually, and then we will solve it uh, through an algorithm. Okay. So suppose uh, this is the tree, the same tree I am taking here. The value is say 5 here, plus the value is say 7 here, and the value is say 3 here, right? Now initially we will start with the root node. We will start with root node, right? Now when we come here, this root node is having either left or right, right? In this case, it is having both left and right. It is having left node, it is having a right node also. Both node it is having. So we will go to the first left node. As usual, we will traverse from the left hand portion. Okay. So when you come to this node, you will come to the 5. Then this 5 is not having any left or right node, right? There is no left or right node. So it will return 5 here. It will return 5 here. Okay. Then it will come to the right hand side, and then it will see here that again there is a node having left or right portion. Okay. So again it will go to the left node, left node, and here returns 7 here. To the right here, what is there? 7 is there. So it will return portion, it will return 3 here. So this left and right, one will return 7, other will return 3, and what is here? Here the operator is there. So we will check which kind of operator is here. Now here is plus. So whatever getting from the left hand side 7, and whatever getting from the right hand side 3, this operation will be performed. Plus will be performed between 7 and 3. So 7 plus 3, 10 will be returned, right? Now when you come back to here, here the star symbol is there, that is multiplication. What you receive from left hand side, you receive 5, and what you receive from right hand side, you receive 10. So now here the multiplication operation will take place. 5 into 10, 50, and the 50 will be given back. So your answer is 50, right? The answer is 50. So any doubt in this? No, it is not on mute. Already I've tested all the things. I've called technician. So he is looking after all those things. There may be some problem. He will solve later on, right? We have checked that thing. The PC is not on mute. Volume mixer, it is high. Uh, no mute is there. It is 100% is there, right? Okay, fine. So any problem in that simple example? Let us consider another one more example, right? So we will have some other expression. Suppose this is say slash, this is say plus, this is say 5, This is say 3. Let us come here, say minus, this is say 6, this is say 2, right? So according to our, what should be the result? 5 plus 3, here the answer should be 8, here the answer should be 4, and 8 divided by 4, final answer should be 2. This answer we should get. So we'll start from the root node. Now root node is not a single node, right? It is having left or right portion. So if it is having left portion, we will evaluate first the left hand side. So we will visit to the left node of this root node. When we come here, again we find that this is not a leaf node. It is having left and right node. So we will come back here. Now when we see here, this node is a leaf node, right? It doesn't have any left or right node. So it will return 5 here, right? And when it calls right hand side, it will return 3 here. So it got it get 5 and 3. And what is the operator symbol here? Plus is there. So it will perform 5 plus 3, 8, and it will return 8 here. So when it goes to the right hand side, again it will find that this is not a leaf node. It is having left right node. So it will call a left node first for finding the value of the expression. This is going on recursively. So it will return 6 here, it will return 2 here, and 6 minus 2, 4 will be performed here, and 4 will be written here. So already we have received 8 here and 4 here. The operation is divide, that is slash. So 8 by 4, answer is 2, right? So you will get 2 answer here. So what is our algorithm? Our algorithm is like that. If the node is a leaf node, right? If the node is a leaf node, return data, right? जो भी data होगा उसका return. Else, what we will do? We will call the left hand side and right hand side. So we will say left sum is equal to, again we will call the same function expression with left node, and we will call expression again the same function with right node, right? So we got left and right, so we will receive here left portion, we will receive here right portion, and then we will check the operator. What we want to check, whether it is plus, minus, star or slash. Accordingly perform the operation. Right? So it will perform the operation and it will return the result. Okay, it will return the result. Like that algorithm will work. So you have to check whether the node is leaf node or not. If the node is not leaf node, you call the function, same function by passing left node, the same function by passing right node. Whatever you get from the left node, you will put in left sum. Whatever you get in right, from right portion, you will store in right sum, and then you will check which operator it is. Accordingly, we will perform the operation and we will return the result. That's all. So any doubt in this? Yes. Okay. Some more students may write. अभी एक नहीं लिखा, और एक दो लिख देंगे तो अच्छा रहेगा. So that I will proceed. Only 2 students have written that there is no problem. Okay, fine. थोड़ा अच्छा लगता है कि अगर मान लो प्रॉब्लम है तो आई कैन रिपीट. Okay, now we will see the code. Fine. Now we will see the code, that how to find out the evaluation of this. The name of the function is evaluate expression tree, right? The name of the function. This screen is visible, na? This code is visible, all of you? Yeah. So first of all, we will check whether the root is existing or not. If the root is existing, then only we'll proceed. If root is none, we will return 0. Directly we'll go back, right? So this won't happen actually, because we will call the function only if the root node will exist. If the tree exists, then only we will call. But still, for safer side, we are checking whether the tree exists or not. If the root node is none, we will return 0. Otherwise, we have to check whether it is a leaf node or not. So if root dot left is none and root dot right is none, if they doesn't have any left or right node, that means it is a leaf node. And if it is a leaf node, we have to pass the data. We have to return the data, as I told you, that if it is a leaf node, you have to return the value stored in that data. So, and then you will find out if it is not a leaf node, it will come here. So again, we will call the same function by passing the left node, and we will get the value on the left hand side. Again, we will call the same function by passing the right node, and we will get the value on the right hand side. And then we will check whether the whether the intermediate node contains plus, minus, star or slash. We are considering here only 4 symbols, that's all. So accordingly, if it is a plus, what we are returning? We are returning left sum plus right sum. If it is minus, we are returning left sum minus right sum. If it is star, we are returning left sum multiplied by right sum. And if it is slash, we are returning left sum divided by right sum. So according to algorithm, what we have done, we have checked whether the node is leaf node or not. If the node is leaf node, we are returning the data. Else, what we are doing, we are calling the same function again by passing the left node, and whatever we are getting, we are storing in the left sum. Again, we are calling the same function by passing the right node, and whatever the right node will return, it will be stored in right sum. And then we are checking which operator is there on that node, because it is not a leaf node, so definitely it is an intermediate node. If it is intermediate node, it will have some symbol or some operator, right? So we are checking operator here. If it is plus, we are doing addition. If it is minus, we are doing subtraction. If it is star, we are doing multiplication. If it is slash, we are doing division. The drawback of this program is that it is considering only 4 operators: plus, minus, star and slash. That's all, right? So if we run this program, what we are passing here, here I will just write down here 2 plus 3 3 4 plus star star star. 2 plus then 3 3 4 plus 3 3 4 plus star star. What is the answer of this expression? Can anyone tell me? Just find out the answer of this. 2 plus 3 3 4 plus star star. This will give 4 3 3 4 plus star star. Then this 3 plus 4, this will give 4 3 7 star star. Then this 3 7 will give 21 star 4, and this will give 84. Yes, the answer is 84. Hmm? Answer is 84. Right? Getting? How the answer is 84? So if we run this program and we run this, the answer is 84. Here you can see the answer is 84. If I change the expression, suppose instead of 2 I am giving 4 4, right? Instead of 2 if I give 4 4, and if I rerun the program, we are getting 168. Why 168? Because here I have written 4 so it will give 8 here, right? 8 here, 8 here, and 21 into 8, it will be 168. So like this, we can evaluate the expression. So the same thing is happening in the real life, right? Whenever you are compiling the program containing expressions, right? Containing expressions such as say c is equal to a plus b minus c slash d multiplied by e, like this. What the compiler does first, it will first convert this infix expression to postfix, right? And then it will create a tree. It will create a tree and then it will evaluate the tree. And then it will return the result in this variable, right? So the application of this kind, whenever you are working with any system level application, right? Whenever you are working with any system level application, you will come across such things where you need to use the concept of tree, right? Mainly, you can again say another example in operating system. You can say means where softwares, high level softwares are designed, right? There you can have a use of this kind of even in application oriented, wherever you will come across, suppose you are developing a software for library, right? So you may have different sections in library, okay? So when you click on this section, you may come across a section, uh, reading section, or you may come across a journal section, like this newspaper section, like this. So in this, a tree is created like this, right? So there you can make use of tree. So in any application where hierarchy is to be maintained, in that case you can make use of tree, right? So any problem so far? So as far as syllabus is concerned, now we have covered the application of binary tree, that is expression tree. The another application is Huffman encoding, right? So we'll see first what is Huffman encoding, right? So any doubt in this evaluation of expression? Otherwise, I will continue with the other topic, that is Huffman coding or encoding. Shall I start with Huffman coding then? Now, yes, please type in chat box. Okay, fine. Now, what do you mean by this Huffman? मेरी राइटिंग ऐसी नहीं है, इससे काफ़ी अच्छी राइटिंग है, लेकिन ये जो पैड है मेरे पास, उसमें जो पेन है उसकी वजह से राइटिंग ऐसी आती है. अदरवाइज इफ आई राइट ऑन ब्लैक बोर्ड, द राइटिंग इज वेरी गुड. तो आपको लगता होगा सबका राइटिंग कैसा है. ठीक है. अब मेनली द टेक्निक इज यूज्ड फॉर डेटा compression. This technique is mainly used for data compression. I think you know what do you mean by compression. If I give you a real life example, right? Real life example, compression का मतलब मान लो आपने पैंट शर्ट, राइट, पैंट शर्ट को आपने वॉश किया और उसको आप प्रेस करने के लिए दे रहे हैं, राइट, आयरन करने के लिए. प्रेस करने से पहले वो कपड़ा जो है थोड़ा फूगा हुआ रहता है, मतलब वॉल्यूम उसका ज़्यादा रहता है, और प्रेस करने के बाद में उसका वॉल्यूम कम हो जाता है. जैसे भी हम कभी सफ़र पे जाते हैं, राइट, तो हमारे बैग में हमने प्रेस किए हुए कपड़े रखे होते हैं. और जब रिटर्न आते हैं तो उतने ही कपड़े उस बैग में नहीं बैठते हैं, राइट? ऐसा एक्सपीरियंस किया है आपने कभी किसी ने? जाते वक्त हमारे सब कपड़े उसी बैग में बैठ जाते हैं, लेकिन आते वक्त वो कपड़े नहीं बैठते हैं, क्योंकि जाते वो कॉम्प्रेस्ड फॉर्म में होते हैं, प्रेस करके रखते हैं ना उनको, तो दे आर इन कॉम्प्रेस्ड फॉर्म। और जब उधर से आते हैं तो दे आर नॉट इन कॉम्प्रेस्ड फॉर्म, और इसलिए इट टेक्स मोर स्पेस, राइट? तो किसी ने जवाब नहीं दिया शायद। ओके, तो कॉम्प्रेशन का मतलब क्या है? टू सेव द इंफॉर्मेशन विथ लेस स्पेस, टू सेव द इंफॉर्मेशन विथ लेस स्पेस, कम जगह पे इंफॉर्मेशन सेव करना। सपोज आई वांट टू सेव दिस इंफॉर्मेशन ए, राइट? कितने बार लिखा मैंने? 1 2 3 4 5 6 7 8। हाउ मेनी बाइट इट विल टेक? It will take 8 bytes, right? It will take 8 bytes. If I write, say, B, 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 so these are 4 bytes. It will take 4 bytes. So 8 plus 4, total 12 bytes it will consume. So, can we find a way to store the same information in less amount of space? किसी के पास कोई आइडिया है इसके लिए? ये समझ में आएगा आपको? मेरे पास डाटा क्या है? 8 बार ए और 4 बार बी, ये डाटा है मेरे पास, राइट? राइट, तो 8 टाइम्स ए एंड 4 टाइम्स बी, राइट? इस तरीके से आप 12 बाइट को कंप्रेस करके कर सकते हैं। तो दिस इज वॉट एवर मिस्त्री धूमिल हैज गिवन आंसर, दैट इज कॉल्ड एज रन लेंथ एनकोडिंग, RLE। इसको क्या बोलते हैं? रन लेंथ एनकोडिंग बोलते हैं, राइट? लेकिन अगर सपोज यही डाटा मेरे पास ए बी ए बी ए ए बी ए 1 2 3 4 5 6 ऐसा है, मान लो उतना ही स्पेस है, सेम ए 1 2 3 4 5 6 7 8 और 1 2 बी, उतना ही है। इसमें भी 8 बार ए लिखा हुआ है और 4 बार बी लिखा हुआ है। नाउ इफ यू यूज द सेम कोडिंग हियर, राइट, इफ यू यूज द सेम कोडिंग हियर, विल इट सेव बाइट्स? अब इसमें क्या हो जाएगा? 1 स्टार ए, 1 स्टार बी, 2 स्टार ए, 1 स्टार बी, 2 स्टार ए, 1 स्टार बी, 1 स्टार ए, then 1 स्टार बी and 2 स्टार ए। अगर if we follow this method, 8 स्टार ए, 4 स्टार बी, राइट? तो अब ये कॉम्प्रेशन हो रहा है कि एक्सपांशन हो रहा है? whether this is compression or expansion, compression और expansion, क्या हो रहा है ये? यस, राइट? कोई कोई लिख के बताइए, तो मिस्त्री आप ही लिख दीजिए। इट इज एक्सपांडिंग, राइट? दैट मीन्स इन सच केसेस दैट मेथड इज नॉट फाइन। RLE हर जगह काम में आएगा क्या? नहीं, राइट? when you are having consecutive number of same character repeating most of the time, then only you will come across such method, RLE। जैसे फैक्स है, फैक्स में कैसा है? मान लो ये आपका पेपर है, राइट? और इस पेपर पे आप कोई इंफॉर्मेशन लिखते हैं एंड देन यू फैक्स इट। तो ये जो पोर्शन है, इतना पोर्शन केवल ब्लैक रहता है, बाकी सब पोर्शन व्हाइट होता है, राइट? So for white you will having say 0, and for black you are having 1. So it will have consecutive numbers of zeros, continuously zeros. Somewhere you will have consecutive number of ones, somewhere you are in consecutive numbers of zeros, like this. So in such cases RLE is okay. But where in a text paragraph, suppose you are having only 2 characters, no doubt, A B B A, but they are not written continuously, right? Instead of that, they are written alternatively, sometimes 2 times, sometimes 1 time. So in such case we cannot use RLE method. But overall, if we see how many characters are there, only 2 characters are there, right? Only 2 characters, A and B. So if you want to store the information of 2 characters, how many space you will require? Can anyone tell me? If I want to store information of only 2 characters, how many space, how much space you will require? A bit, byte, 2 bytes. No, don't now talk in terms of bytes. Only two information. You can talk in terms of bits also now. Because we know that A is there and B is there. But for storing only two type of information, how many bits you will require? Suppose I say that a student is either pass or fail. So for pass, I will write say 1. For fail, I will write 0. So how many bits you will require then in that case? For pass, I will require 1 bit, and for fail also I will require 1 bit. This 1 bit will write an 1 and this one will be 0. So if I write 1, I will assume it as a pass. If I write 0, I will assume it as a fail. So if I am having say 8 students in my batch, 8 students, right? I'm what I'm trying to do, I'm writing a byte here, 8 bytes. And if I write information like this 1 0 1 1 0 1 0 1. So from this information, can you tell me how many students are pass and how many students are fail? I can say 5 students pass and 3 students fail, right? Because there are 5 ones and 3 zeros. So in 1 byte, I can store the information of 8 students, whether they are passed or failed, right? है ना? So this is something which you might have studied in your communication, which is called as entropy, right? Does anyone know entropy? The amount of information, right? So if you are having only two pieces of information, you can store in in 1 bit. If suppose I am having 3 categories, one is pass, other category is fail, and the third category is not appeared. Third category कौन सी है? Not appeared, right? So now for such kind of, how many bits you will require to store this kind of information? So you are in 3 categories: pass, fail, and not appear. So how many bits you will require to store each information? Even now you can you say 1 bit? अभी भी 1 bit बोलोगे? क्योंकि 3 information है ना, pass, fail, not appear. 3 information. So in 1 bit you can store only 2 information. 0 for something and 1 for something. 0 for pass, 0 for fail किया था मैंने, 1 for pass. What about not appear? In 1 bit you have only 2 possibilities. So I have to take 2 bits. So I will have 4 combinations: 0 0 0 1 1 0 and 1 1. So I can say 0 0 means fail, 0 1 means pass, and 1 0 means not appear, and 1 1 means don't care, right? I can say like this because I am having 3 information with me now: fail, pass, not appear. So this 3 information I can store in 2 bits. What is the formula? It is simple, that you are having 3 information. So 2 raised to 2 is equal to 4. So you can, in 2 bits you can store 4 information. So in 2 bits you can store 3 also. One will be not here. If you are having 6 information to be stored, you will require 3 bits because 2 raised to 3 is equal to 8. In this case, 2 fields will be not applicable: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So last 2 won't be applicable. This is 0 1 2 3 4 5. 0 to 5, 6 information you can store in 3 bit, and with 2 as don't care, right? Getting these things? समझ में आ रहा है मैं क्या बोलना चाह रहा हूँ? Yeah. So now my question is there. Suppose you are having a sequence of characters with you, say A, B, A, B, C, D, E, A, B, C, D, E, D, 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 E, A, B. They may represent something. I don't know. We don't care about what they are representing. They may represent that. Now there are five cases. You can see here there are five symbols. So there may be five cases here. E, 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 A, 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 B, B, and then E, 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 E. I'm writing too many E's here because all the students are first class. Right? For example, like I'm writing like this. Okay. So if this is the text, now suppose I'm not counting, right? Just I'm assuming that these total numbers are 60, right? 60 characters are there. I'm not counting, maybe wrong, but I won't waste my time in counting this. I'm assuming that there are 60 characters. That means the frequency of plus frequency of B plus frequency of C plus frequency of D plus frequency of E. What will be this value? This value will be equal to 60. Now here A may appear 5 times, B may appear 10 times, C may appear 7, D may appear say 15 times. So what will be the value of E? 5, 10, 15, 15, 30 और 7, 37 हो गए ना. So this will be I think 20 right times 5 plus 7 plus 5
Yes, sir. 23.
17 plus 3 22 4 5 6 60 right. So this is the frequency that how many times A is occurring, how many times B is occurring, C, D and E is occurring. Now I want to assign codes for this. How many symbols are there? 1, 2, 3, 4, 5. Now, if the same logic we are applying here, once again, that for storing 5 information, how many bits you will require now? Can anyone tell me? For storing 5 information, how many bits you will require? 3 bits, right? Okay. So, this means 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0. Suppose I am giving A here, B here, C here, D here, and E here. Means here I am giving fixed length. What I am using here? Fixed length of coding. Right? Fixed length of coding. So how many bits I will require then? Suppose A is 5 times, so 3 5 are 15 bits. Then this is 10, so 30 bits, 7, so 21 bits, 15, so 45 bits, and 23, so 69 bits. Overall, the sum will be 180, no doubt, because total are 60, each is having 3. But if you see here that the frequency of A is very small, still you are giving 3 bits to them, and the frequency of E is very large, and still you are giving the same piece of bit. To A also we are giving 3 bits, and also we are giving 3 bits. Can we think of that if I am able anyhow to give 1 bit to A, right? 1 bit to E, sorry, 1 bit to E. So I can store instead of 69, I will require only 23 bits, right? Because the frequency of E is 23, right? And if I am giving say 4 bits, if I'm instead of 3, if I give 4 bits to A, right? 4 bits to A, then what will happen here? It will consume 20 bits, right? 5 times it is occurring, so 5 4 is 20. And remaining, if I say, okay, they will be as it is. So they are say 30, 21, and 45. So if we do the total, 5 plus 1, 6, 3, 9, 2, 3, 5, 2, 7, 4, 11 to 13. So it is consuming only 139 bits, thereby saving 41 bits, right? Because here we are taking 180 bits, for example. But if I assign variable length of the coding to the symbol having low and high frequency, here A is having low frequency, I am giving more bits to that A as compared to E, because E is occurring more time. So if I give less number of bits, I will be able to save more bits of information, right? So if I can do, or if I am able to assign variable coding to the characters instead of fixed size coding, I may be able to save some more space, because the characters are not evenly distributed, because the probability of the occurrence of the character is not evenly distributed. Yes, if you know that every character is having more or less same kind of frequency, then fixed length of coding is best one, no doubt. But if the frequency of the character is not same, it is uneven, in that case, then we may try to go for a variable length coding technique. And that variable length coding technique is called as Huffman, because Huffman is using the concept of variable size of code, right? So this is just an introduction that why we need Huffman, right? So how actually the Huffman works, that we have to see. How the codes are assigned by the scientist whose name was Huffman, because the name is given after his invention. He has invented this method, that how to assign the codes to the information, right? So we will see. And the technique which Huffman has used, it is also called as prefix code. It is also called as prefix code. Now, what do you mean by prefix code? Suppose I have given code 0, 1 to A. I have given code 0, 1, 0 to B. I have given code 1, 0 to C, right? If this is the coding scheme given by me, right? Now, if suppose I am having the bits like this 0, 1, 0, 1, 0, 1, 0, if I have written like this, now when you will read the first two bits 0, 1, and you will check, yeah, this is for A. Write A here. You have read 0, 1, you may write A. Now again you will write 0, 1. So what you will think again? Oh, again A is there. Then again you will read 0, 1, and you will come to conclusion, okay, A is written there. And then when you will come to the last 0, you will see that 0 code is not given to anything. So it will be question mark here. Actually, what I have done here, I have written the code for ABC. For A, I have written 0, 1. For B, I have written 0, 1, 0. And for C, I have written 1, 0. Right? But because you have assigned the codes in such a way where this code, suppose the code for B already exists in A, because B is containing 0, 1, 0 and A is containing 0, 1. So the prefix portion of the B is already given to the A. So this is not called as prefix code, because here what is happening? Some portion of the code of another symbol is assigned as a code for another symbol. So instead of like this, instead of this, if I assign code like this, A 10, B 01, and C 11. Suppose like this, and then if I write 10, 01, 11, right? So when you read first one, you will come to know either it will be A or C. But when you read next 0, 10, you will confirm that it is A only, right? Then when you read 0, you will be here, and after 0, when you read 1, you will see that it is D. And then when you come to the next bit 1, you will see whether it is A or C. It will be confirmed that the next bit is 1, so it is 1 1, so it is C. So in this way, a unique decoding will be there, right? In this case, unique decoding will be, because here the codes are not a part of prefix. Any code, if you see, that code is not a part of other code. 100111. These are not the part of other codes. You may have some like this also. A is equal to 1, B is equal to 0, 1, C is equal to 0, 0, 1, D is equal to 0, 0, 0, 1, like this also. So even if you say like this is an example of prefix coding, because कोई भी portion prefix का किसी दूसरे का part नहीं है. So the prefix codes are created. Prefix codes are created using Huffman technique. Prefix codes are created using Huffman technique. So how they are created, कैसे create करते हैं, ये सब हम देखेंगे हमारे next lecture. We will see in next lecture that how the Huffman algorithm is used for creating the tree, how the codes are generated, and how the generated codes are by default the prefix codes, right? And how with the help of such kind of coding we are able to save the space, amount of space which is required for storing the data, right? So we will finish lecture here. I will take first attendance. आज की तारीख है 15. All of you, happy Engineers Day. So A division 1, 2, 4, 8, 9, 11, 12, 13, 15, 16, 18, 20, 21, 22, 23, 24, 25, 29, 30, 33, 38, 40. B division 1, 2, 4, 8, 10, 14, 16, 17, 20, 21. Fine. So thank you. We will meet tomorrow and we will see how the Huffman tree is created. Meanwhile, you can also see the books and you can also go on the internet and search how Huffman trees are created, so that you will have some kind of knowledge about the creation process, and we will see tomorrow and we will see program on that also tomorrow. Thank you.